Okay, welcome to Monday's lecture. This would be Monday, 24th of June, 2013. Today we are studying sections 5.6, 5.7 as those are the homeworks, two homeworks that will be due on the 25th. So far, we have studied in this chapter about work, kinetic energy and the work energy theorem, which was section 2, the gravitational potential energy, spring potential energy, and then energy conservation within certain systems. Lots and stuff about energy. And now we're going to actually take it a step further and talk about power. Well, power is to energy what speed is to distance, right? You go a certain distance in a certain amount of time, and then you can calculate an average speed by taking that distance divided by that time, you get an average speed. And power is energy divided by time. You use up a certain amount of energy, or you dissipate a certain amount of energy, or you transfer a certain amount of energy, or whatever you do it in a certain amount of time, and it gives you what we call power. And this is the thing that we hear of quite a bit, actually, in the real world. We hear about the power plants, and we hear about the power required for this, and we hear about this and that, taking so much power, and the power crisis, and the cost of electrical power, and whatever else. This is the power that they're talking about. This is exactly that. Since power is a measure of energy per time, then it's going to have units of joules per second. You can see that down here, joules per second. And we call that the watt. It's a capital W, and it's the watt. And the definition for power, average power, is work done divided by change in time. And it can be any kind of work, really, but it can also be any kind of energy at all, really. If the work being done is mechanical work, then it's going to be equal to force times a distance, and you're going to get F delta x over delta t, where the delta x over delta t actually becomes an average velocity. So if you're applying a force to something that has an average velocity of whatever, then you can just multiply the force that you apply to the object by the average velocity, and that would be the power, or the average power. Of course, you can also have instantaneous power, in which case you would have to know the instantaneous velocity. So here's a breakdown of the units of power. 1 watt is equal to 1 joule per second. And since the joules are equal to kilogram meter squared per second squared, then watts are equal to 1 kilogram meter squared per second cubed. However, in the United States, again, we use a different unit for power often, in certain cases, called horsepower. We use this particularly in the car industry. Excuse me, but we also use it in other industries. And it turns out that 1 horsepower is 550 feet-pounds per second, which is about 746 watts. So you can see that a horsepower is a fair number of watts. It's almost a kilowatt. Now what would happen if we multiplied power, which is 1 kilogram meter squared per second cubed, but if we multiplied this by time, we would get back kilogram meter squared per second squared, which is energy. And we use that quite a bit when we're measuring energy used in a house, for example. We call it the kilowatt hour. And what a kilowatt hour is essentially is a kilowatt that has been used for 1 hour. So you're using an average of a kilowatt over the time of an hour, and that is a kilowatt hour, and it happens to be about 3.6 million joules, and your average household actually uses a few of these a day, probably, these kilowatt hours. It's a measure of energy, again, not power, because kilowatts are power, and hours are time, and power times time is energy used. So we use that quite a bit, the kilowatt hour. Let's take a look at a elevator motor delivering power to lift an elevator. In this example, we have 1,000 kilogram elevator. It carries a maximum load of, 800 kilograms. There's a constant frictional force, slows it down as it's going upward, but minimum power in kilowatts and horsepower must the motor deliver to lift the fully loaded elevator car at a constant speed of 3 meters per second. Well, they draw the force diagram for us. We have the tension in the rope going upward, we have the friction going downward, we have the weight going downward. So there's our force diagram of the elevator. And they're going to go ahead and apply Newton's second law here in the first step. The sum of all the forces equals the mass times acceleration, and since this car is not going to accelerate, it's going to go at a constant speed. The acceleration will be 0, so the right hand of the equation will be 0, but we'll have 3 forces to add together on the left-hand side of the equation. That's a start. Then, since all those forces are going in the same direction, the only thing we care about is the signs of the forces. We don't care about any other vector quantity of them. So we just take the signs. The tension force is upward, the friction and the weight are downward, and that has to equal 0, which means the tension force has to equal the friction force plus the weight force. And we solve that for tension. And then you just plug in the numbers we have for the weight, mass times gravity, and the frictional force which they give us. We get a tension force of 2.16 times 10 to the 4 newtons. Well, why do we need that? We need that because the tension force is the force that is moving the elevator. And on the previous page, we discovered that power is equal to force times velocity if the power comes from mechanical energy, which it does. Mechanical work equals force times distance, and divide that by time, you get force times velocity. So the velocity we just calculated in the previous, or the tension that we just calculated in the previous section, 2.16 times 10 to the 4 newtons, can go together with the velocity to give us 3 meters per second to give us 6.48 times 10 to the 4 watts. Well, it turns out that that is about 64.8 kilowatts, and 64.8 kilowatts can be converted into 86.9 horsepower using the conversion on the previous page, which was approximately 1 horsepower per 700 watts or something like that. That's power for you. What about the Shamu Sprint? The killer whales. Killer whales are known to reach 32 feet in length, have a mass of 8,000 kilograms. They're very quick. They can accelerate to 30 miles per hour in a matter of seconds. Disregarding the considerable drag force of water, calculate the average power a killer whale named Shamu with mass 8,000 kilograms would need to generate to reach a speed of 12 meters per second in 6 seconds. So, we need to know this power. They've given us, so far, what have they given us? They've given us a final speed. They've given us a mass. They've given us time, right? So we're doing good. A final speed, a mass, and a time should get us somewhere, something somewhere. They go ahead and they use the kinetic energy equation here. And we have the change in kinetic energy is equal to kinetic energy final minus kinetic energy initial. And the initial kinetic energy starting from 0, so they just calculate the final kinetic energy, which is 5.76 times 10 to the 5th joules. And that actually tells you how much change there was in the kinetic energy, which tells you how much energy you had to provide to make that change, because this is going to be equal to the amount of work done. And so 5.76 times 10 to the 5 joules divided by 6 seconds is going to be work divided by time, which is power, average power. 9.6 times 10 to the 4 watts is the amount of power needed to accomplish that. So can we go down on the page here? Speedboat power. Okay. Often used with speedboats is the horsepower. We have a 1,000 kilogram speedboat. That's a pretty heavy speedboat. It must be a big one. Needs to go from rest to 20 meters per second in 5 seconds. So now they've given us a change in speed again, a mass again, they've given us time again. Well, this sounds like it's going to be a very similar problem. And then they also tell us there's a drag force, so we have to include that. Acceleration is constant. So we go in here and we say that the work net Remember, work net includes things like friction equals the change in kinetic energy equals 1/2 mv final squared minus 1/2 mv initial squared again. Again, we're starting from 0 speed, so the initial is going to 0. But on the left-hand side of the equation, we have two types of work. We have work done by the engine and work done by the drag force, the frictional force here. And remember that one of these is going to be positive, one's going to be negative, because one's going to be pushing one way, one's going to be pushing the other way. I would say that the work the engine does, we'll call that positive. It's making the boat go faster. Work the friction does, or the drag force does, is going to be negative, taking energy away from the boat. Right? So we go ahead and we throw all this stuff that we have in here. Well, we don't throw it in there. Let's just save that aside, actually. So we're going to need some other things. We need to know, for example, we're going to want to know eventually the displacement, because remember the work is equal to force times distance, where power is equal to force times distance divided by time, right? And so we're going to need a distance traveled. So we use a kinematic equation. This kinematic equation will give us, from here, to give us the final velocity. Then we can use that final velocity in the next kinematic equation to get the delta x. That's exactly what they do. Solve for the final velocity first, using the acceleration and the time. Then they use the acceleration and the final velocity, find the change in x from this second kinematic equation. Now that we've got everything, the drag force is going to be force delta x. So we put in the force here, we put in the distance, and we get negative 2.5. Remember that friction force we decided to be negative anyway. The work done by the engine has to be equal to the kinetic energy, the final kinetic energy, which is the change in kinetic energy. But you're also going to have to put in this drag force. Now it looks like they're subtracting it, but remember the drag force was a negative number to begin with. So we're actually adding the drag force here. And why would it need that? Because the engine has to both overcome the drag force, it has to overcome the friction by putting that much energy back into the boat, but it also has to put out enough energy to do the accelerating or maintain the velocity or whatever it's doing in this problem. So once we get the work of the drag worked out here, we work out the work the engine does, and we get 2.25 times 10 to the 5th joules. And then we take the power, which is the work of the engine, divided by delta T, and we get 4.5 times 10 to the 4 watts. Convert that to horsepower, 60.3 horsepower. Part B, symbolic expression for the instantaneous power. Well, Newton, let's see, we got here. Here they start with Newton's second law, which is force equals mass times acceleration. And then they solve that for one of the forces, because they have two forces involved here, Fe. And we've got that here. And then they actually calculate the power using Fe times V. And they plug in for Fe, ma plus Fd times At. And here you get this equation that is time dependent. You can actually calculate power as a function of time. So you can find it at any time, instantaneously. Kind of nice. Let's see, what else do we need to put in there? I think we're good. Okay. See, I think we missed something. Yes, we're on the next subsection, I guess. Energy and power in a vertical jump. Well, it turns out that when you're jumping, you're using your biochemical energy, and you're going to turn it into kinetic energy until you reach the top of your jump. And then it's slowly, as you're reaching the top of your jump, it's slowly being turned into gravitational potential. And there's definitely energy being passed around as you jump. And one thing that you want to be careful of, though, is that human beings, of course, are not points. They're not very simple objects. They've got a lot of weird things to them. And so often what we do is we try to measure a center of mass, which for most people is right around their waistline, and usually right just below their belly button, or somewhere thereabouts. But we do all of our measurings from the center of mass, and that way, stretching of the arms and the legs doesn't affect your jumping score. They actually work out the potential energy, kinetic energy initial, plus potential equals potential energy final and kinetic energy final here for this problem. And you can see here that kinetic energy is going to be mgh, and they solve for h in the end. I mean the potential energy. The kinetic energy on one side equals the potential energy on the right hand side in the end, because initial potential energy is 0, initial initial potential energy is 0, and final kinetic energy is 0. So you have just kinetic equals potential. And then you can start plugging things in. They've actually measured the height as a function of the center of mass velocity over 2g. And you may remember that I mentioned at one point that jumping is all about speed. So the faster you take off, the higher you go, the farther you go, whatever. It's going to be the case. So you'll see that these athletic jumpers are all about speed in their jumps, not power or anything else. Now, if you have some initial velocity at center of mass, you can go ahead, of course, and calculate the height that you're going to reach. So in this case, they take off at 3.2 meters per second. You square that divided by 2 times gravity, and you get 0.52 meters, half a meter.